Welcome back to Statistical Methods. This is week 13, lecture 2, and this will be the final lecture for this course. Now, just one announcement. Course evaluations are live, so please complete these as soon as possible. And now, let's start off with a little recap. Last class, we discussed the chi-square test of goodness of fit, which allows us to test whether a set of observed frequencies deviates from some set of expected frequencies to a statistically significant degree. Now, remember that the key distinction between this and previous tests we learned is that here our dependent variable is categorical, as opposed to an equal interval numeric variable, from which things like means and variances can be computed. Thus, each individual score will be a category membership of some kind, for example, as for gender, race, or religion, as opposed to a quantity, like a person's age. And the numbers we end up analyzing aren't individual scores, but rather frequency counts within different categories. As the goodness of fit test only involves a single categorical variable, we can ask about the extent of fit or mismatch between observed and expected frequencies, but do not have any independent predictor variable to help explain or predict patterns of category membership. For example, I might find with a goodness of fit test that the gender breakdown in this class significantly deviates from chance, or a 50-50 split, but I couldn't say anything about why this might be. Now, the solution is to incorporate info from a second categorical variable that allows us to either elaborate on a causal relationship of some kind, if this variable is experimentally manipulated with random assignment, or simply describe the association or relationship between our two variables, if this variable is simply measured but not manipulated, like with correlation or regression. In analyzing the relationship between two categorical variables, there are two possible outcomes. Possibility one is that these categories are independent of one another. Knowledge of a person's score on the first variable, gender, does not give us any greater ability to predict their score on the second variable, religious affiliation. In other words, these variables appear to be unrelated to one another, similar to the interpretation of a R of 0 in correlation. Now, possibility two is that these categories are dependent on one another. So knowledge of a person's score on the first variable, for example, gender, does give us some ability to predict their score on the second variable, or political affiliation. In other words, these variables are related to one another, as the male-female ratio differs on a basis of political party. Somewhat analogous to the dependency of an interaction effect in factorial ANOVA, a difference in differences. The difference between male and female frequency counts differs on the basis of political party. The question of independence or dependence between two categorical variables is tested with a chi-square test for independence. And conducting this test involves determining first what the expected frequencies would hypothetically be if our two variables were independent or unrelated, so the null hypothesis, which is different from the goodness of fit test, now only one possible set of expected frequencies. And we also have to collect data to obtain our observed frequencies, then quantify the mismatch between these two for each combination of categories with chi-square. Determining whether this mismatch is sufficiently large to reject the null hypothesis that our variables are independent of one another. So note that the name of this test is a little misleading. A statistically significant result in this case actually reflects dependence, not independence, between variables. And this is tested against a null hypothesis of independence. Thus, our result will either be p of less than 0.05, statistically significant, meaning dependence between our two variables, or greater than 0.05, or equal to 0.05, non-significant, or inconclusive, potentially indicative of independence between two variables. So imagine we wanted to examine the gender split between two different professions, doctors and lawyers. So categorical variable 1 is gender, male versus female. Categorical variable 2 is profession, doctor versus lawyer. And using a chi-square test for independence, I can test the research hypothesis that there is some dependency between these two variables. In other words, is the male-female breakdown different for doctors and lawyers? That's our research hypothesis. Or are these two things independent of one another? In other words, is the gender breakdown the same in both professions? So we begin by creating a contingency table that displays our observed frequencies across these two categorical variables in a sample of 2,000 doctors and lawyers. So this is a 2x2 contingency table. We have 670 male doctors, 600 male lawyers, 330 female doctors, 400 female lawyers. And here we have the sums across these two rows, and down here we have the sums across this column and this column. Now, calculating the row percentages for the male-female split, collapsing across profession, we have a male-dominated sample. 63.5% of the sample is male, whereas only 36.5% of the sample is female. So, does it seem like a gender breakdown depends upon profession? Yes. There is a higher male-female ratio for doctors here than for lawyers here. But is it different enough to reject the null hypothesis that these variables are independent of one another? To answer this question, we need to figure out what our expected frequencies would hypothetically look like for each possible combination of categories if these two variables were actually independent of one another. So what would independence look like in this case? Well, if these categories were independent, then the proportions up and down the cells of each column should be the same as the overall row percentages here. So our total percentage of males and females are 63.5 and 36.5. Thus, if gender is independent of profession, we should expect to see 63.5, 35 split in both the doctor and lawyer columns. So we would expect 63.5% male, 36.5% female, and the same here. So our expected frequencies in these categories are independent. So our expected frequencies, if these categories are independent, would be male doctors, so 1,000 times the percentage expressed as a decimal point, 635, or 635. Female doctors, 365. Male lawyers, 635. Female lawyers, 365. And note that our estimates end up being the same across the two professions, only because we have the same total number of doctors and lawyers, 1,000 each. Usually this won't end up being the case. Thus, we end up with an observed and expected frequency table for these two situations. Now let's set up these two variables in Excel to make our subsequent calculations easier. Now, for the sake of this lecture, I'm going to do this directly in the PowerPoint, but you can use Excel to do this on your own if you would like, using the skills that you've learned through this class. So from there, the procedure for testing whether our observed frequencies significantly differ from the expected frequencies, indicating dependence between our two variables, involves the same steps as the goodness of fit test covered last time. For each cell, each combination of categories, of which we have 4, calculate the deviation of observed from expected frequency, square that value and divide it by the expected frequency for that cell. And then sum across these cells to get chi-squared and determine whether that chi-squared is statistically significant. And here it is with all the math worked out. And once and when we sum up all these values, we get 10.58 as our chi-squared value. Now, the degrees of freedom for a chi-squared test of independence is the number of columns, which we have 2, minus 1, times the number of rows, which we have 2, minus 1. So that's 1 times 1, which equals 1. And then plug this into the same Shiny app that you did last time to find the cutoff value with a significance level of 0.05. And the cutoff value we get is 3.84, and our chi-square is 10.58. So we can reject the null hypothesis, conclude that there exists a dependency between the variables of gender and profession. Note that neither of these variables was experimentally manipulated, thus similar to correlation. We can say that these variables are related and use one to predict the other, but not that one causes the other. Now, a number of effect sizes can be calculated for a chi-square test of independence. One standardized measure of the effect size for a dependency between two categorical variables is known as Kramer's phi. And this is calculated by dividing your chi-square test statistic by the sample size multiplied by the degrees of freedom for whichever variable has fewer categories. So the df of the smaller one. And then taking the square root of this. And Kramer's phi ranges from 0 to 1 and can be interpreted in line with Cohen's cutoffs below, which depend upon the degrees of freedom for the smaller side of the contingency table, same number you just used in the denominator for the calculation of the effect size. And that's all I have. Thank you for being great students. Please fill out the evaluations, and good luck on the final exam and the remainder of the class. And please refer to the calendar to figure out exactly when things are due. And this is, again, the updated calendar that I posted last week.